hybrid emulation, accelerating software-driven verification, and debug. Time to market abstract. Time to market is one of the key factors in the semiconductor industry, not only for commercial success, but also meet the technology demand of today's world. This can be achieved through a highly optimized verification strategy, including early-stage software development and testing. As the size of the complexity of the design increases, it is no longer possible to load the whole design into the emulator, especially where the OS boot and software applications need to be validated. This is where the hybrid emulation fills the gap. Debugging and hardware and software issues using the real OS app on the FPGA-based Juno platform was challenging due to low design visibility. Hence, it takes a significant amount of time to root cause the underlying issues. Hybrid system consists of virtual platform connected to the SoC sub-block GPU running in the emulator. It can run the full software stack and the GPU graphics and the compute content with full design visibility. Now it is easier to reproduce and debug and find and root cause of the software and hardware issues reported in FPGA platform. The hybrid platform also enables faster design bring-ups and the verification closure. The introduction. Traditionally, the ARM GPU software and hardware and software verification was performed in the FPGA-based platform, which is a silicon-level SoC board with an onboard FPGA where we physically map the GPU. Even though the runtime throughout the high for this FPGA platform, the lack of design visibility and the difficulty in extracting the trace dump affected the debug time. This motivated us to bring out an architectural equivalent hardware emulation platform using hybrid technology. Hybrid emulation is a custom FPGA or processor-based technology based on different EDA partners, which is different from the FPGA prototyping. With the hybrid platform, where GPU running inside an emulator, we can reach a full design visibility, which was lacking in the FPGA platform. Since RTL CPU is replaced by the C-based models, fastmodels and virtual CPU models, and we got a faster boot time. Since software stack runs in CPU main memory, it makes the entire execution of any application faster while maintaining the full accuracy of the last of SoC. We can greatly improve simulation performance, allowing us to boot up an operating system and executing a functionality on the accurate model of the SoC and in a significant shorter time. This enables the development and verification of drivers and kernels and applications, validation with the firmware of the SoC way before silicon tape-out, and GDS2. Chapter 2 is a motivation toward the hybrid platform. The hybrid platform is spring up was motivated by the limitations of the existing FPGA platform. The major challenges we have to address were the prolonged debug time due to the poor design visibility and difficulty in getting the traces. The complex real OS app issues could take weeks to generate the stimulus and reproduce at unit-level simulation platforms. The GPU hardware and software live debug is challenging in existing platform. Issues reported in different verification platforms and tools are typically not closely reproducible. In addition to that, the hybrid platform becomes the best way to shift left the hardware-software co-verification, allowing us to perform software development and verification even when the RTL of the critical block isn't available. It gives us the much easier platform upgradability when there is a need of changing the configuration or moving a latest CPU subsystem. It is much more convenient and quicker to execute the software and workloads rather than waiting for the hardware board to be ready. The figure 1 represented the internal FPGA platform where the CPU subsystem and other SoC prefers are in silicon. FPGA-based Juno platform. Chapter 3 is hybrid platform integration. On this hybrid platform, we replace the ARM Cortex-A55 CPU RTL core with its corresponding fast model along with the GIC600 and the smart memory. Replacing this RTL block with the fast model not only helps achieving runtime throughput, but it also reduces the hardware footprint. The RTL running on the emulator will be connected to this virtual platform through TLM transaction level modeling and bridges which provide a communication gateway between the virtual and RTL. This transistor bridge provides a thin layer of BFM plus proxy models where we can connect the RTL port to BFM and software transactions to proxy side. We also use a shared memory of the CPU and the rest of the system implemented specifically for hybrid usage, and we usually term it a smart memory. Smart memory will be visible to the virtual as well as RTL side, and it allows our CPU to access to the memory throughout the backdoor, not via the TLM channel. With this implementation, the CPU subsystem can access to the memory with the virtual system without crossing RTL boundary. Similarly, the GPU on the emulator will access the memory through the RTL channel. Therefore, the software execution will be faster as there is a minimal cross-boundary communication required. At some point, if there is a sync required between the fast model and emulator, it is done using clock pulse of emulator to pass the architecture state of the CPU and a cache memory data sync with the rest of the system. Overall, if there are frequent transitions done between virtual platform and the emulator, it will degrade the overall time performance. Figure 2 shows the virtual platform on the left side connected to the RTL platform on the right side. The virtual CPU, GIC600, and smart memory and other IPs are connected to the virtual router bridge. The other end of the router is connected to the TLM transition pipes coming from the RTL platform. So the router on the virtual side is an EDA vendor-specific interconnect, which can be configured to define the number of masters and slaves with address spaces and etc. of the virtual components. The GIC600 have been moved to the virtual platform, leaving GIC BFM on the RTL side to have port-level connection with the NIC. The virtual router is connected to the CC5550 on RTL through which the virtual CPU access the last of the prefers on the RTL. The smart memory is extended to have a localized memory for CPU within the virtual platform. The Figure 2 hybrid platform block diagram. There are built-in models available by EDA hybrid toolchain to take care of RTL to virtual change in form of the transactions to from CPU. Internally, these models use the scheme DPI to transfer data back to transfer data back and forth the TLM channel across a boundary. To validate the integration of above system, we booted the Linux and ran multi-bare metal tests to access the GPU registers and smart memory. Later, we booted the Android 10, Debian Buster 11, as well as a different graphic test. The hybrid methodology was especially efficient for high-level software use cases such as booting Linux, Android, Linux driver, and different tests that run on the top of these operating systems. Also, it is recommended to maximize the transaction size and minimize the use of high-traffic transactors to achieve best runtime performance. Chapter 4. Runtime performance and result. The hybrid platform helped reproducing the hardware and software issues captured in FPGA platform by rerunning the same test with the functionality accurate hybrid model with full design visibility. This significant reduction in debug time helped fixing the software and hardware bugs much earlier in the verification cycle compared to the previous project. The table 1, hybrid runtime throughput. The figure 3 shows the graphic test running on hybrid platform after the Android boot. The on a Linux boot benchmark moving from the legacy full-RTL emulation to the hybrid platform brought us a 45 times improvement in runtime. The figure 3 is the graphic test running on Android 10. Chapter 5, Debug Capabilities. The EDA deliverables around the hybrid virtual component of ARM CPUs provide additional utilities to debug CPUs such as detailed logging, TLM transition level model visualization, register viewer of CPU, memory map viewer of CPU, and smart memory debug tools, etc. The RTL CPU consumed a clock cycle to execute its state machines along with the rest of the subsystem, whereas the hybrid CPU is running in a synchronous manner in zero simulation time. In this case, virtual CPU can be of non-deterministic behavior with the rest of the subsystem in RTL to debug and replicate any issues in consecutive runs. To overcome this, the hybrid capture replay feature enables more efficient debug by recording stimuli along with its execution and replaying it in consecutive runs and debugs. The hybrid capture replay feature captures or records the input from the virtual platform against the design clock and enables you to replay those input to design in a subsequent session. Apart from the CPU, debug of the rest of subsystem is done using native methods such as RTL monitors and waveforms and memory dumps and so on. Chapter 6. Next steps. We observed the significant gain using hybrid usage in emulator, which led us to explore and deploy it on bigger ecosystem of the ARM, notably on the latest family of the related CPUs and some unreleased ones. ARM has a variety of the use cases where it is essential for the CPU to be cyclically, but hybrid caters an effective co-ownership of FPGA-based challenges in software development. Therefore, it is certainly not a complete replacement of our validation mindset. We also have plans to help using this work and the infrastructure space, server, or enterprise, where a complete becomes system visualization on real emulated hardware is gated by maximum emulator size. Okay. Thank you for your time. I read today the hybrid emulation, accelerating software-driven verification and debug, the DVCON paper. Again, thank you for your time and see you next time.